Okay, so today lecture 5, and we are going to...
А ты можешь еще на экран растянуть, что будет, если нажмешь на эту две стрелочки диагонально сверху, смотри.
Ну, я могу вот...
Да, вот так вот лучше всего. Можно
Ага,
так?
ага,
И
вот
вот
так.
приблизить, да, вот так вот вообще.
Ага, хорошо.
У нас не видно маленький кусочек самого верха, поэтому самый верх не пиши.
Хорошо, хорошо. Да.
Для выхода из полноэкранного режима.
Ага. Хорошо. So, okay, today I'm going to discuss the equivalent definition, I would say, of topological recursion in terms of loop equations and the projection property. And I'm going to prove that the original definition of topological... Okay, the original definition of topological recursion as this huge formula with residues is equivalent to the loop equations and projection property which we had from the previous lecture. So, okay, what we had? Let me write down the loop equations and projection property again, and then to prove something. So today. So that's so projection property. Let me maybe projection property is equivalent to the TR. So what we had? We had this linear and quadratic loop equations, which are linear loop equation states that omega gn of say z1, z2, etc., zn plus omega gn of sigma I z1, z2, etc., zn is holomorphic near holomorphic near zi pi where what dash to
Z1 to pi, you said Zi to pi.
Yes, thank you very much. Where sigma I is an involution. Involution near.
We independently require that omegas are symmetric, so which means that
sorry, I'm just let me finish the sentence. Yeah. Okay. Thank you. Is an involution near PIs and has a yes, an omega and has a simple pole, at least a simple pole at z1 is equal to pi.
Simple zero.
Oh, simple zero. Yeah. At least a simple zero. Yeah, and has at least simple zero at z1 is equal to pi. Yes. So it's true that independently. So in fact, we didn't properly discuss the properties of topological, the properties of omega gns of this and differentials, but the one of the most important properties of this omega gns is that it is symmetric in all its arguments, which you have already seen in the examples. That it. So yes, the
Can I just say something quickly? It's if you look at the right side of that above equivalence, this symmetry is a property. So if you start with the original definition of topological recursion, you get that you can prove that the answer will be symmetric. And on the left-hand side, if we formulate it like this, like here, then I think we need to independently impose the requirement on symmetry. Or do we not?
yeah. So yes, you're right. Yeah. So it's if we're in the setting that we have initial definition of topological recursion, that it is a so important property, say, of original definition. Definition of omega gen. So original residue definition of omega gens. Yes, that they are symmetric. And yes, if you're right that if we are, so I have to state this as a property of this omega gen, or of the set of differentials omega gens. Yeah. Okay, so we have also quadratic loop equations, which more or less the same. So we have the statement is the same, that omega. So maybe I should. Okay, okay, it doesn't matter. Okay, as in the previous lecture, we had a little bit different notations, but it doesn't matter. Z2, etc. Zn plus this sum, which you, I think, know by now. E j omega g1 plus 1 w z I omega g2 j plus 1 sigma I of w zj. Yes, and again it's so this expression is golomorphic, and has at least a double zero, and has at least
At W tends to pi.
what?
It's golomorphic.
Yeah, and at least double zero at W. I don't know, pi. So golomorphic W to pi. And for each all this linear loop equation and quadratic loop equation, this condition should be satisfied in each zero of dx. So this py, as usual, we have dx is equal to 0, x is equal to p1, etc. Z is equal to.
You can write it as Z in. Yes.
So yeah, we have in general n zeros of dx, and this p capitals are zeros of dx.
Recall that we only wanted simple zeros.
Yes. This guy, because of we have this sigmas here. Yeah, as usual. We in the setting of simple zeros of dx, and also we have projection property. Um, projection property. And we state it in a bit maybe not very easiest, not the easiest, in not the easiest way. We stated it in the previous lecture, but in fact, let me today also write it in the same way. But in fact, the meaning of projection property, which we also discuss later, that this omega gn, so the meaning that omega gn of z uh, it has poles only in this p1 etc pn has poles only in p1 etc pn. At least it is true, it is equivalent to the projection property for rational spectral curves. So for if spectral curve is CP1, it is an equivalent statement as projection property, and we will discuss it later. But you may the meaning is the following, yes.
Maybe could you write for CP1? The meaning is
Okay,
for
okay.
CP1.
For CP1, yes. For
And sigma is equal to CP1.
yeah, for sigma. So now we have sigma like okay. I do not quite remember. We had sigma. No. We had sigma as a 4 tuple. So okay, for
So I think
spectral
sigma. Did we? I think
curve.
we used it just as the curve.
If you look in the seminars list, in the problems list, then we have yes, and the projection property, how we defined it, stated the following: that omega gn of Zn, when I'm writing z with index n in these square brackets, I mean that just z1 etc zn. I think you, in fact, you do not see. Do you see me like my picture, my video or not?
I only see what you're writing.
Okay. Then my like my hand waving, you don't see. Okay. Then the projection property states that this omega gn is equal to something which were some residue, the following residue. So with some overall possible ways to like, so okay, for with some overall zeros of dx, residues in these points on w1 is equal to pe1, whereas wn is equal to pi n small. So the n small residues, so we have n variables, n form, and differential here, of integrals of omega 0 2 etc omega 0 okay, let me write omega 0 2 of from pi1 to w1, yes, etc. So times pin small wn omega 0 2 dot zn, then times, so then times omega gn of wn. Okay. Okay, and here this bracket. So we take residue of this form, and then take this n residues, and then sum over all zeros of dx. So they're like partitions of zeros of dx, and the statement that we start with omega gn of w's and obtain omega gn's of z. And again, this, so we will see that this just means that this omega gn's has no poles away from this p1, etc., pn. Yes, and again, we according to this to this statement, I want to be that my omegas has one more condition on my omegas. So this, that say meromorphic, I don't know, 1, 2, 3. Okay, 1, 2, 3, and then 4, that omega gn of z for, say, stable cases. Yeah, so for g greater than 0 n greater than 1 and to g minus 2 plus n greater than 0 are global meromorphic.
Actually, the numbering was different last week, so it was the first. So this condition was the first, and
okay. A global meromorphic symmetric.
Unstable. Yeah. Okay. Anyway.
Differentials. Okay. Yes, and also we have the conditions on the unstable cases. Yes, that say 5 omega 0. We have omega 0 1 of z. It's y as usual.
Well, maybe for consistency, change the numeration that it agrees with what
I think it doesn't matter at all.
Okay, but
I will not use these numbers. Okay, so these 5 conditions, yes, on how it. So yeah, these 5 conditions on omegas, and the theorem is that if we have the set of omega gn such that all these 5 conditions are satisfied, so 1 to 5 satisfied, if and only if omega gn are reproduced by our recursion, topological recursion. So omega gn reproduced. Oh, okay, satisfy. Omega gns, they satisfy TR. It means that what does it mean? Satisfy TR. It means that we have this huge formula in residues. How I don't know. Should I? Maybe I will not. Maybe I do not write down now this residue formula, but you probably probably remember something like that. This omega gn. How did we, in fact, write it? Okay, maybe now for me not something like this. This is a sum overall.
Z0 and then Z bracket n.
Okay, so n plus 1, yes? N plus 1, Z0, Zn. Yeah, thank you. Sum and then residues, and then we have integral something 0 2, then here we have something like this. So it's not the it's not the explicit formula, but yeah, and something like something here plus this sum with prime.
It becomes explicit if you multiply it by minus 1/2.
Minus 1/2. Not, yeah. Something like this, yes? Okay, and now I'm going to start with... Yes, any questions? So this is...
the statement of the theorem clear? Okay.
Okay, and now I'm going to prove this stuff. I'm going to prove from left to right at first. So we have these 5 conditions, and we will obtain this this formula, which I didn't write. Okay, and so proof. Okay, let me at first define so-called, I don't know, symmetrization and anti-symmetrization operators. Maybe, okay, it doesn't matter. So as if I have one form in one variable, then define, so let lambda of z is a one form, then define s of lambda of z. It is lambda of z plus lambda of sigma of z, where sigma, so where we have again simple pole, a simple zero of dx, and sigma is a holomorphic involution, and the delta of lambda of z is lambda minus lambda of sigma z, and I will need a few consequences of these notations. Say if we have two one forms lambda and mu, then we have the following, that lambda of z times mu of z plus this guy, okay, is just 1/2 of delta lambda. Let me skip the arguments here. So delta lambda delta mu plus s lambda s mu. Okay, I suppose it is more or less evident, yes? So are you agree with this?
Yeah.
So you see that all other stuff are just disappears, yeah.
Delta and S, and this statement.
What?
Все понятно?
Ну, вроде бы я что-то слышал, что...
Нет, все в порядке, да, я просто спросил.
And yes, the second is the...
Одну секунду.
Are letters C different or the same?
Where? Here?
Yes.
The same.
Что?
The question was in this right formula on the right. Is that the same?
Yes. Okay, and the second one that this say skew sum. Yes, so here z and sigma of z and sigma of z and z is equal to the same expression with minus. Okay, delta mu of z minus s.
You can just directly substitute the definition of delta and s and see that.
So
We should
okay.
have one minus there.
Where?
Because the right side equation is with minus now.
Yeah, so here we have minus, yes, but I hope. So see. So you, okay, so you want me to write a bit about this?
No, I just think that they're not equal right now, they're minus equal.
No, let's see. Then this product will give, say, okay, this is lambda of z mu of z plus. So okay, let's track the sign of this summand. Yes.
Just for brevity, maybe let's write lambda for lambda of z and lambda tilde for lambda of sigma of z.
Maybe, but no. Let's track the sign of this summand. Yes. Here, in this guy, it is this with plus. Yes, lambda of z times mu of z because of yes, and here it will appear also with plus, and this minus will kill this summand. Are you agree?
По-русски быстро скажу, у нас же в симметризаторе все слагаемые с плюсом, в антисимметризаторе 2 с минусом. То есть те, которые не сократятся, они будут с минусом и в антисимметризаторе, и с минусом и в симметризаторе. То есть у нас все будет с минусом, а слева все с плюсом. Правда? С минусом не согласен?
Да. Все, что не сократится, будет с минусом.
Короче, правую часть надо на минус домножить еще.
Вы хотите сказать, что все с плюсом сократится, а останется все с минусом?
Да.
То есть вы хотите... Сейчас, странно. Сейчас, давай, хорошо.
Может, неправда, но кажется, что если скобочки раскрыть, действительно минус должен быть.
Да, наверное, вы правду говорите, да. То есть если вы... действительно, если посмотреть на какой-нибудь... Соответственно, вы говорите, если посмотреть на лямбда от z, мю от сигма от z, вот на это слагаемое, да, то она тут отсюда придется минусом, отсюда... Да, действительно. Окей. Sorry.
Сережа с Гайтаном нам наврали.
Да. So let me then write it. So we again find a mistake in the classical papers. Minus delta minus. Okay. Okay then. I just wanted to define these notations. Okay, and now I want to rewrite the projection property, this expression from the projection property. And let me now, so let me say the following, that it is because of symmetry of omega gn, and because of the form of this expression. In fact, we can define operators in each. So we can like obtain this n residue independently, and residues independently in each variable w1, etc., wn. So I want to define like the projection operator in one variable, and all other variables keeping the same. So let me say define p1 of omega gn of say z1 and all other guys z2, etc., n is as a sum over all ramification zeros of dx. Again, I take one residue as I had here w to pi, and then this integral, okay, from pi to w. I have only one now, w, omega 0 to dot what I had here, z1, yes, z1, omega gn of w, yes, of 1w, w and z2, etc., n. So again, I want to like divide this huge operator here into n independent operators in each variables. Okay, and I want to prove. Okay, we'll see how it goes, but in fact, it doesn't matter. So because of the symmetry of omegas and the structure of this projection property operator, it works well. And okay, so maybe no, it doesn't matter. Okay, I state that this expression is equal to the following. So let me rewrite it. Now, what is the, okay, let me say what is the plan maybe. The plan is the following. Now I want to, so I know by projection property that this is equal to, in fact, omega gn of z1, etc., zn. And I want to rewrite the right-hand side, and then use linear loop equation and quadratic loop equation. And so, in fact, we will have some omega gn is equal to something. And in fact, this something, this something, I want to rewrite in the form of initial definition of topological recursion. So the logic is very, so I mean the general logic is very simple. So we have this equation, and we want to rewrite the right hand side in to see that the expression in the right hand side coincide with the expression of initial definition of topological recursion. Okay.
P1 preserves this omega gn. We know that the combination expression of all the P1 and so on Pn.
Petya, could I can't hear well.
So the question is, why does P1 preserve omega Gn when we said that the composition of P1 and so on Pn preserved it?
Yeah, okay, because of, so let's it because of it these operators are so these operators act independently in each variable. So if you maybe maybe we should discuss it now, that yes, okay, let's look at this. So we have, yes, we have P, so we know that projection property means that P1 etc. Pn, yes, it's how it's written here, of omega Gn of yes, omega Gn of Wn is equal to omega Gn of Z. Yes, and if yes, and I want to say that it's just equivalent to the following, that we have that how, let me write.
P1 omega is equal to omega.
Sorry?
You can just say P1 omega is equal to omega.
Yes, P1. Okay, so yes, maybe so let's look at this expression, and what's the easiest way? I think let's rewrite this integral of omega 0 2, so from pi to w z1. Yes, we have. So what is it, in fact? It is so in fact it is pi w say d z1 d dot over.
We are in this sigma equals to CP1 case.
Yes. Yes, but okay. Maybe I should write here. Yes, I should write here that for today, for this semester, we have. Yeah. So what is it? It's something like 1 over. So it's 1 over z1 minus dot from pi to w. So it's 1 over z1 minus w minus 1 over z1 minus pi. Yes.
Should have
Or
minus.
No, if you write
No.
one minus dot, then it's okay.
no, something.
I think it's correct what you wrote.
It's correct. Yeah. Okay. It's correct. And then I obtain here p. Yes. So w minus pi over Uh, I'm afraid that the sign is incorrect. Yes.
No, the sign is correct. You forgot dz1. dz1.
Yes, dz1 I forgot. Yes, the sign is correct.
I think so.
Okay. Okay, and then so you should take the what's the statement that you take residue Dun, dun, dun. Omega gn w z2 etc n w p1 and okay, so we should maybe it's easier to see if we take, so what we want to see that if we take two such
I think in this question that why it's enough to consider just one.
yes.
Know that all the PIs they act independently in.
Yeah. So that's what I want to.
It's symmetric. So that means that. So first of all, in one direction is obvious, right? If you have just in one variable, this is true. Then it's obvious. So you just apply this iteratively, and you get what's written, right? In the direction from downstairs to upstairs, it's completely obvious. The statement, right?
So let me. I just wanted to write it more explicitly, and then I think it will be evident. Yes. So we have something like this. Yes. We have something like this, and and we know that we know that this is equal to omega gn of Zn, and in fact we really can apply these residues consequently. Yes, and these two residues are absolutely independent from each other. Taking these two residues, okay? Is now it's so. Did I answer your question? It is now is clearer than before.
Not very convincing.
Okay, how to maybe a bit more explicit say this? Okay, taking the first. Let's see what is happening when we are taking the first residue. Then these maybe I will write in such a way. So this residue, then this part just will stay the same because it's different variable W1 and it's just independent of W2, and we just work with this part, okay? And okay, so you okay, let me say the following. If we already know, let me for one moment so say that we know already that this projection property is equivalent to the statement that omega gens have no poles except of the points p1, etc., pn. Then I think it's obvious because this statement does not. So and then I could say that this p1. I have misleading notations. So this p, let's say p. P bolds, then it's, I hope, obvious that P1 means that this omega gn has okay. No, it will not help. Yes, it will not help in such a way. What should I? So in fact,
residue, we will get something more summons, for example, that will be killed by other residue.
No, but the point is that this, in fact, cannot happen because omega is because each of those PIs acts on the ith variable, and moreover, the whole expression is symmetric.
yes.
If you think about it, you can see that this what you're saying cannot happen.
What the suggestion was?
That after we apply the first residue, we will get some more
Some
summons.
additional term, okay.
Yes, some additional terms that will be killed by other residues. Why?
No, it.
No, the question is, so what if here we have some additional term on the second line?
Yes.
Some additional term, which is then after you apply, let's say, for instance, in the situation when we have only two variables.
Yeah. We have, okay.
Can it happen that we have, after we apply the first residue, we get some additional term, then we apply the second residue, and this term gets killed. And you get that the first line holds, but the second line is not correct.
But
you need to take into account that P1 only acts in W1, and P2 only acts in W2. And moreover, you know that omega is symmetric.
Yeah, so if these summons will appear in the after the action of as a result of action of P1 bold, P2 bold, sorry, then it will also appear in the action of P1 bold, and then in the result we will not have this guy.
Okay, yes.
Because yes.
Because it's symmetric, then you will necessarily get this summon again when you apply the second residue. But it's not there. So then it cannot be killed because you do not apply anything after that. So look at the last one. Suppose the first action of P adds some additional term. Okay, but then look at the last one. It should act the same term, but in a different variable.
Yes.
It's not there. You only get the same omega. So then this means that it's equivalent.
So
So is it clear at this point? Sorry for a little bit of confusion, but is it clear that indeed this is equivalent, those two things? If you take into account symmetry of omega and the fact that pi only acts in the variable wi. Okay? So in this direction, it's obvious. So you just iteratively apply this. And in this direction, assume that there is some extra term here after
here.
that.
So yeah, after this, yeah. Oops. After this and this, yes.
But then, and it might get killed by applying the other piece. But let's look at the outermost p.
Yeah. Then it also produce the same terms for W1.
It should be equal to omega, meaning that this term shouldn't be there. But here you use the fact that it's symmetric and the fact that it acts in wi variable only.
So okay, is it better now? Or not?
Is better.
Okay. Okay, then we have this P bold 1, which is equal to this guy. And I want to continue. So it is equal to the following. It is, in fact, equal to the following. So, and now I have the following 1 over 2. Yes, sum from 1 to n residue in P, and then this. So maybe okay, it doesn't matter. These integrals pi w omega 0 2 of dot z1 omega gn of w z2n plus of sigma plus the same maybe let me write this instead of this integral. Let me write this expression. Yeah, maybe it will be more. So we have just this expression, yeah, here, w minus p1 yes, and plus sigma of this guy. So I want to write so sigma of w minus pi over sigma of w minus z1 pi minus z1 pi minus z1 dz1 and omega gn of sigma of W Z to N. Yeah, so why? So instead of what's happened now? Instead of this just this product of integral of omega 0 2 and omegas, I write this sum, and here I just write. In fact, this guy is just say integral of omega 0 0 2 of sigma of dot z1. So yeah, I applied this holomorphic convolution. So the question is why it is true. In fact, I would say let see on. So if you think, so what we know the linear loop equation, and the linear loop equation says that that this sum is golomorphic, and that this sum is golomorphic. Then no, 1 second. So I want to so we know that this is omega gn, this is omega gn of and this is as a sum golomorphic, then okay, so is it, I think, so we know that yes, so okay, it I think it works as follows. So we know that this is by the projection property, this is omega gn, yes, and so we have the sum of two residues here. So this is omega gn. This is the second residue of the second sum. The second summand is omega gn of sigma, omega gn of sigma of z, z2, etc. n. So and this, the whole guy is holomorphic, and therefore the so it should coincide. Yeah. So one second. It was. So we have what we have. We have something. Yeah, we have. It should be more or less evident. So again, we have this guy here, and
Вы 2 раза применили. Одно для
No.
всей, а другое вот для каждой отдельной омега-ЖН. И там 2 раза минус появился, и он сократился.
Сейчас, мне казалось, я прошу прощения, мне казалось, что это должно быть как-то очевидно видно из линейного уравнения. Хорошо, давайте на минуточку поверим в это. Let me skip this step.
Нет, мне кажется, что ты правильно уже начал говорить.
Да, но что-то не сходится в конце у меня.
Вроде сходится, потому что когда мы применяем P1, то у нас вся голоморфная часть уходит. Вот.
Когда мы применяем P1, то вся голоморфная часть уходит.
Да, мы пока не знаем, где голоморфная часть.
Ну да, сейчас. Мы только знаем, что это омега Gn просто от Z.
Запишем его уравнение. Оно говорит, что омега Gn плюс омега от сигма.
Да, вот это голоморфно, да.
Это что-то голоморфно. Тогда это означает, что...
То есть мы знаем, что правая часть вот этого равенства, которое мы хотим понять, голоморфна, да.
Но мы теперь, с другой стороны, можем сказать, что если мы хотим записать... Давай выразим, значит, омега Gn это будет минус омега Gn от сигма плюс что-то голоморфное, да?
Да.
Значит, тогда можно сказать, что запишем как сумму таких двух штук с одной и второй.
Да.
А теперь запишем такое выражение, что омега Gn равняется 1/2 омега Gn плюс еще 1/2 омега Gn.
Угу.
И в одну из них, из этих 1/2 подставим омега Gn от сигма.
Угу.
Плюс-минус сейчас разберем.
Тогда это равно 1/2 омега Gn минус 1/2. Ну вот да, с минусом. У меня проблема с минусом возникла.
Разберемся. Может быть, минус здесь тоже... Может, он должен быть. И теперь ко всему этому применим P1.
Да.
В левой части мы заметим, что это равно омега Gn снова, потому что P1
Да.
от Gn это омега Gn. А в правой части это будет P1 от whole обратиться в ноль, потому что whole...
Да, теперь мы должны заметить, что действительно P1 от голоморфного в P1 дает 0, потому что это вычет в P1. Хорошо. То есть, ну вот у меня вот с этим минусом была проблема. То есть получается, что должен быть минус.
Ну, сейчас разберемся.
Да, ну хорошо, попробуем написать тут минус. Okay, do you agree with this вывод? Вы согласны, что если я тут напишу минус, то все сходится? Или ничего не понятно, что произошло? So, again, we just use linear loop equation and rewrite the omega Gn in a bit stupid way. Like we said that because of linear loop equation, we know that omega Gn is equal to minus omega Gn of sigma of one variable plus some holomorphic stuff. And on the other side, omega Gn is equal to 1/2 omega Gn plus 1/2 omega Gn. And here, instead of this, I write this here and obtain this summand, and then take residue, take P1 of left-hand side of this, and P1 of holomorphic just disappears, and we obtain that P1 of this is equal to P1 of this, and this is just what is written here, here, and here. Okay?
So I don't understand. So we have in the formula for P1, we have W as a limit of integral.
Yes.
И мы вроде на него никак не влияем.
Еще раз, да?
У нас W сверху есть.
Да.
У нас W есть как предел интегрирования верхний. И от того, что мы поменяли омегу, он не поменялся. Соответственно, вот тут вот, по идее, должны остаться W, а не сигма W.
Почему нет? Мы пишем...
Сейчас вот это вот буквально формула. Это правильно? Вот.
Да.
Ну так и что?
А почему туда вот вместо W поставили сигма W? Вот это не очень понятно.
Почему мы туда... Сейчас.
В смысле, что вот здесь...
Да, справедливый вопрос.
Да, хорошо. То есть, почему я вот тут вот так написал, да? Сейчас, действительно, я хочу... Сейчас, секунду.
Давайте, может быть, так сделаем. Сейчас сделаем, у нас все равно должен быть сейчас перерыв. Давайте, может быть, сейчас...
Сейчас, все-таки еще 10 минут.
Не, правильно, но я предлагаю, что мы сейчас, может быть, сделаем перерыв, а потом раньше начнем, и с этим...
Ты хочешь взять технический перерыв? Сейчас, ну давайте, подождите, но... Вопрос про сигма. Хорошо, вопрос про сигма. Ну давайте я напишу. Я могу... So I can write as follows. I can write here instead of this guy, instead of this integral. I just can write, say, something. Say g of dot z1.
Oh, this is g of w z1.
G of w z1. Yes, g of w. Okay, then. So no. Okay, yes, but what's the question? Yeah. It's so I was wrong here. Yes, somewhere. So it's okay. We have sigma of w in the limit of the integral. Yeah, it's okay. So yes, I want to write this as.
No, but I mean how we did it in the if you look down there, we only we took omega of sigma, but in P1 you need to multiply it with g, and
yes, and this g of sigma of you mean that
yeah, maybe not P1 of omega g and W1. Just W to it.
Давайте сейчас сделаем перерыв, потом продолжим после перерыва.
Сейчас, то есть вопрос в том, что тут это рассуждение не работает, потому что тут сигма есть.
Да.
Потому что разные P1 жирные.
Там стояло G-W.
Да.
Все правильно поняла, что мы вначале заменили вот так, потом применяем лимит P1.
Да, хотим теперь применить к обеим частям P1.
Сигма будет Z1, потому что мы же взяли от сигмы, от Z1. Тогда у нас нет, то есть мы взяли вторую, это омега GN от сигмы от Z1, тогда вот там должно быть V минус P1, V минус сигма от Z1 и P1, P-ита минус сигма от Z1. К сигма применяется к тому, она не должна, у нас теперь к Z1 применяется сигма не должна.
Сейчас.
Давайте разберем сейчас, давайте сделаем перерыв до 14:45. Все независимо подумают над этим.
Хорошо,
Да?
давайте так.
Сейчас, это не совсем типа, то есть, что мы берем просто, когда вычет вычисляем, заменяем переменную просто. W, сигма W.
Кстати, да, может быть, действительно.
Тогда и плюс получается, и все нормально.
Да.
Ничего использовать не надо.
Да, так на самом деле, действительно, да, вы правы, да.
Что еще раз скажите?
Это сделайте при вычислении вычета, там берется интеграл. В этом интеграле заменим просто переменную. Вот этот интеграл заменит переменную W на сигма от W.
Хорошо. Сейчас, на вычет это...
В интеграле, который вычисление вычета.
Да, я понимаю, да. Сейчас и на вычет это никак не скажется.
Но сигма W это тоже локальная переменная.
Да.
Так что вычет можно считать так, можно так. Ну, хотя, а может нет.
Давайте сейчас аккуратно посмотрим.
Ну хорошо, давайте...
Хорошо, 14:45.
Да, хорошо, давайте тогда я остановлю пока запись. Okay, so finally sorry for for the pause. So we actually understood the following, that to prove this equality, yes, it's only needed that the sigma is an involution. So, and the statement is the following: if sigma an involution, then in fact the residue of some form alpha is equal to residue of alpha of sigma of z, and it's more or less evident. So the proof is here. That if so we can take and then if we know this, yes, then this is just we take this residue and the same this residue, and instead of one residue we write 1/2 of two equals residues. Yes. So it is just like rewritten in terms of like a is equal to a half of a plus half of a. Yes. And so why this residue, two residues are coincide? Because of this proof, and just take as it's written here, just choose a local coordinate.
So here alpha is just any one form.
Yeah. Alpha is any one form. So take a local coordinate, say W, such that it's 0 at P1 and involution is just a minus W. Then if alpha in the local coordinate is Laurent series, then the residue is equal to C minus 1. Then alpha of Z is this Laurent series, and the residue is equal to minus C1. So the residues are coincide, and therefore all works. And here again we obtain this. So we use this statement for this alpha. Okay.
So is it clear now?
Okay, for people from online, are you agreed with all this stuff? Yes. Okay, and then let me again rewrite this blue line as follows. So maybe let me in fact write instead of this instead of these, maybe let me write g of what, of sigma of w z1, yes. Then what is it here? In fact, is omega of sigma z times g of sigma of z. I mean this, and this omega of just wz and g wz. So this is exactly this. So let me rewrite this blue line as the right hand side of this equation. Okay, so it will be 1/4 1/4 sum from 1 to n residue w to pi. So s, yes, s. Say, let me write s1 g okay, I should here I'm sorry, here should be sigma I, yes, sigma I, and here should be gi, okay, and this gi of sigma of w z1 times times s1 omega gn. Oh, sorry, without sigma, yes. W z1 s1 omega gn w z2 n plus, yes, plus here. So I just now I'm writing this stuff. Plus delta 1 gi of gi of also w z1 delta 1 omega gn omega w z.
Maybe let's use SW and delta W because S1 and delta 1, it's not clear what this one is.
Yes. Yeah, okay. So this means that we use symmetrization and anti-symmetrization in this variable W, in the first variable W, yes. Okay, so is it clear? This step, just again some strange rewriting.
We just substitute the definitions of delta and S, and immediately again some terms cancel, and then you immediately obtain what you got above.
Okay, now what was our plan? So we want to use a quadratic loop equation, and let me rewrite quadratic loop equations also in terms of.
Maybe first use the linear loop equation to get rid of the SS term.
Yeah. So in fact, the linear loop equation says that something is golomorphic, and in fact it says that this is golomorphic. So in fact, where we have our S. So in fact, the linear loop equation says that this stuff is holomorphic. Yes.
Well, once you apply it to omega.
Sorry.
If you apply it to omega.
Yeah. In fact, if you are in our setting, and so and here therefore this guy is holomorphic and this guy is holomorphic. Therefore, they killed by taking a residue. So, so it is equal to 1/4 some residue.
Because multiply is not common.
The first one.
What?
You mean this one?
Yes.
It's yeah. You actually know that this guy is holomorphic and also has at least a simple zero. And once you multiply it with G, this does not contribute to the residue. Okay.
Yes.
Yeah, I think it's you cannot. What I think you cannot indeed say that as G is holomorphic, but it has at most a simple pole.
But oh yeah. Sorry. I mean, this guy is golomorphic
and has a zero.
and has at least a simple zero. Yeah, and this
has at most a simple pole.
And this guy has at most a simple.
Where was our formula for G?
So here, just here. So
Yeah.
you mean that
For W equals P. No, but I can't. It's not. It doesn't even have a pole, right? So G has also a zero.
at
W equals P.
W equals P, we don't know, in fact, because of.
Oh yes, so we have.
Well, yeah. Okay. I mean, sorry. G. Yeah. Sorry. G is this guy. This guy.
Yeah, and it is holomorphic. Sorry, so I wasn't.
Yeah, and it's golomorphic. Yeah.
You're right. Sorry.
Yeah. Okay. So it's G of Z. Z1. Yes. Yeah. So
they're both holomorphic.
Yeah. Okay, because holomorphic use. Okay, and then let me rewrite quadratic loop equation in terms of S and delta. And quadratic loop equation in terms of S and delta looks as follows. So what does it mean? That this guy is holomorphic. So we have here this product of we have here.
Well, maybe you can copy the whole equation down.
Yes. But okay. So let me exclude from the second summand this summands with omega 01 times omega gn.
There as some prime plus the rest.
Yes.
Do you remember what was sum prime? We write the sum as sum prime plus two terms actually. There will be two extra terms. And we will explicitly write them.
So
let's denote this expression as QGM.
let's see if we'll need it. Okay, so this
I think it will be easier.
maybe. So this is omega w z2 zn plus omega 0 1 times omega 0 1 of w times omega g n sigma I of w. What? Sorry. G n plus 1, I suppose. Zn plus omega 0 1 of sigma of w and times omega g n plus 1. Oops. Okay. Plus omega 0 1 sigma of w times omega g n plus 1 w zn plus sum prime. Okay, so sum prime is this sum without these two summands. Yeah. Oops. Okay. And you see here this and this. It is again this. So say lambda of z times lambda of sigma of z plus lambda of sigma of z times mu of z. So we had what we had here, yes, and this is SS minus delta delta. So I write here is equal to omega g minus 1 and plus 2 w sigma of w z to n is equal to SS minus delta delta. So S omega 0 1 of w S SW, yes, SW omega g n plus 1 w zn minus delta y plus so as usual, as before, omega 0 1 of w delta w omega g n plus 1. So is it clear? Yes. Yes. No. Yes. No. Plus sum prime. 1/2. Yes. Somewhere should be 1/2. 1/2. Yes. This is the quadratic loop equation. Yes. Okay. So and then let me look at this. So what we see here, and oops, and what we see here. I want to again rewrite this delta, this line delta delta, this line, and what it will be using these. It will be the follows. will be so okay, maybe let me rewrite. So what we had? We have 1/4 some residue w to pi, and we have only this delta delta w g I w z1 delta w omega g n. Okay, and so this is equal to what? 1 second. I want.
So you express delta delta
Yes.
as in terms of the whole the rest of the thing. So that's why I wanted to denote this by Q. So we denote this whole guy by Q, and you say that delta delta is equal to Q minus.
But yes, but 1 second.
Here is delta G, delta omega.
Yeah, okay. So let me maybe, let me.
You need to divide by delta omega 0.
Yes. Let me write a bit more. Yes, so this, I should, so this is, okay, and this is the quadratic loop equation, and then we have the following. If let me denote this stuff, as QGN, and then I have that
It's not clear what you denote by QGN. The whole thing.
all this, the whole this is QGN, and then then delta W omega G n plus 1 W Z W Z n is equal to QGN minus some prime minus omega G minus 1 n plus 2 omega sigma I omega. So now you see, yes? So I just want to express these in terms of the others. And I denote all this sum as Q. So it's Q minus all this stuff and divide by this. What else?
Minus 1/2 SS.
Minus, not minus.
Yes.
No, stop. This is equal to what? So I'm wrong. Yeah. So here is minus.
Yes.
Plus and plus 1/2 SW omega 0 1 W SW.
Yeah, delta was also with 1/2, so you need to actually say that it's.
Delta is also with 1/2. So yes.
So it's two times Q plus sigma.
2 times 2, and here no 1/2. Yes, thanks.
And minus 1 also.
1 second. Cn 2 over. Phew. Okay, now I plug this guy here.
Omega, maybe you can write that omega gn was equal to this.
Not this, but omega gn. Okay, yes.
No, I wanted to, yeah.
Okay. This is omega gn of Zn. Yes.
This is what we proved before, right?
Yeah. And omega, and therefore, and now we plug. So plug. Say 1, 2. Say plug 1 into 2. The left hand side into left hand side of 2. And so what we have omega gn of z. So does someone is still here with us?
Subtle in one you have omega gn plus 1.
Yes. Now I will rewrite.
Так, всем ли понятно, что происходит?
Да, вообще понятно ли глобально, что происходит? А дальше вопрос, понятно ли локально, что происходит?
Еще раз, мы вот уравнение 2 мы получили, применяя свойства проекции и линейное петлевое уравнение. Да? Помните? А уравнение 1 мы получили, это просто выражение, по сути просто выражение для квадратичного петлевого уравнения. Для того, что входит в квадратичное петлевое уравнение. Мы пока еще не использовали даже, что вот это QGN голоморфно имеет квадратичное.
Да, мы просто вот здесь вот, значит, сейчас, что было сейчас после перерыва? Давайте я повторю. После перерыва мы сначала поняли, что первый переход был тривиальный. Дальше мы поняли, что можно переписать через S-дельта и сократили половину, потому что она голоморфна. Дальше я последние, не знаю сколько времени, переписывал квадратичное петлевое уравнение. Даже не квадратичное петлевое уравнение, а просто само выражение из квадратичного петлевого уравнения через S и дельта, чтобы выразить из него вот это выражение. И теперь я это хочу подставить, в то, что вот сюда. Вот, только тут действительно единственная проблема сейчас, что тут все обозначения поехали, потому что у меня тут вот здесь выражение для омега gn плюс 1, а здесь омега gn. Но это я сейчас исправлю, только надо будет единственное, что у меня QGN будет разные вещи обозначены за QGN, но, наверное, мы переживем.
Два проще два переписать для n плюс 1. Давайте просто два исправим.
Ну, давайте, да, хорошо. So let me rewrite 2 in terms of omega gn plus 1. So I just have to write here n plus 1, here zn, and here n plus 1, and here n plus 1. Okay. Then omega g n plus 1 z n plus 1.
Maybe let's do it like I suggest writing z0. So here.
Then I should.
No, because I mean now you have a problem because you have omega g n plus 1 on the left hand side. You have omega w z1. Yeah, this would be better.
Then.
Well, so in the argument of g, it should be z0.
Yes, and
w z0, and now it's correct.
And now w zn.
There is a square bracket missing.
Yes. Okay. Hope that all is okay. Is equal to. So 1/4 some residue delta w g I w0 over delta w omega 01 w.
Okay, one moment. Does anyone recognize this ratio?
times.
Is it similar to something which we had somewhere else? What
Yeah,
is the-
I want to remind that what is lambda delta of alpha of z is equal to alpha of z minus alpha of sigma of z.
And what is G? G was this integral. Of
Yeah, and g,
Дельта не было, но там было
Вот это раз.
интеграл от сигмы от z до сигмы. От G это интеграл от P до z. Когда вы берете дельта, это и есть просто в точности интеграл от сигма от z до z. So is it clear that this factor, this ratio, is precisely the one which you had in the formula, in the original formula for topological recursion, just written in terms of delta? Is it clear? Okay, sorry.
yeah, thank you. So let me maybe write here 1 over 2. So I have here 1 over 4. I write here 1 over 2 and should divide everywhere here by 2. So I have then 1/2 of this stuff, yes. Oops. 1/2. So okay, let me maybe at first write the rest. So I have omega g minus 1 n plus 2 w sigma I of w z to n plus sigma plus some prime minus q gn and plus 1/2 s. So what is remain to do is we should understand that all the last two summons disappear.
By as red, by red lines or something like that.
Yeah, z n. Okay, so we should understand that these guys disappear. Yeah.
Once you take the residue, they do not contribute to the residue.
Yeah. And if we will understand it, then we're done, because of this is just what is written in the definition of topological recursion. This is some prime, is our sum prime. This is this first summoned omega g minus 1 and plus 2, and this is the prefactor which we already discussed now. Yeah, so this should disappear somehow. Yes?
So is it clear that if these two guys, if we prove that they do not contribute to the residue, then we're done? Okay.
Okay, so is it, do you agree?
Okay.
Полина, Rafael, Leonid. Yeah, okay. Not okay. So and it's in fact obvious because of what about QGN? QGN is a expression for quadratic loop equation, and what we know that it is golomorphic, and moreover it has at least or 0 of order 2 at omega is equal to p1. So after at first thing what we should discuss about this denominator. This denominator, I state that it has a simple pole at omega is equal to pi. Yes, a simple zero. Sorry.
So double zero, I think.
Double zero. It has double zero. Yes, it has. This guy has a double zero, and the whole prefactor has a simple. Should have a simple pole. Yes.
But we need to discuss why no more than double zero for the denominator. So there is additional requirement that critical points of y and x should not coincide.
Yes. So let me write maybe. So again, this guy.
The denominator will have only double zero, but not a higher order of zero. This follows from the requirement that pi should not be critical for y.
Okay, let me, Petya, let me write it down. Yes. So
yes.
At first, the numerator. This guy has a double. So this G has a simple pole.
Simple zero.
No. Pole. Yes.
Zero.
Simple. Sorry, simple zero. Simple. Yes. This guy. This G has simple zero, and this delta of G has a double zero. No, the delta also has a simple zero. Yes.
Mm-hmm.
Yeah. The numerator. So let me write it down. Yes. So delta W G. Oops. G I has a
So maybe
simple.
you can write explicitly. I think it will be useful here to write delta WG.
So we have this.
This guy, but is applying delta to it.
So we have this. Okay, so it's no, okay. I think it's clear that it has a simple zero. No.
And we had the formula on the first lecture, I think. For
Yeah, I mean it. So is it clear that it has a simple zero? So W z null z0.
it's maybe you can write that it's dz0 of times the sigma I of W minus W. Could you write the formula for delta G?
So yeah, I mean, so we have delta, we have G. I mean, for what reason?
Just to see what happens. Just delta G, the numerator there, is equal to, we computed it already on the second lecture, it's dz0 is equal to dz0 times dz0 times in the numerator sigma I of W minus W times the ratio, so in the numerator sigma I of W minus W.
Maybe.
And divided by z0 minus sigma I of W times z0 minus W. Of W, sigma.
Yeah.
Times z0 minus W.
Yeah, something like this.
And we see that indeed what happens when W tends to pi, because sigma is the evolution at that point, so sigma I of pi is equal to pi. So we have a simple zero due to this numerator.
Mm-hmm.
Is it correct? Yeah, sorry, maybe with an overall minus.
Maybe, but yeah. Okay, so and the second is that the denominator, this delta W omega 01 has a double zero.
But not high, double zero, but not a higher.
Yeah. Just double zero at W is equal to P1 Pi. So why? Because of is equal to x of z dy of z.
Why?
Oops.
Yeah.
Hey, it's a professional deformation. Sorry.
It's XY duality.
Yes. Minus y of. And the statement is that zeros of, in fact, zeros of dy are away from zeros of dx. And, oh, sorry, it's of w should be everywhere. And again, so P1 is a zero of dx. Yes.
But not Y.
Yeah, but not of dy. And therefore, 1 second, and why we have here double zero.
1, 0 comes from y minus y of sigma, and 1 comes from dx, because it's a 0 of dx.
Y minus. Ah, okay, yes.
And we also require that it's a simple 0 of dx. Said that pi is a simple 0 of dx, and because it's not a 0 of dy, this means that y of w minus y of sigma of w has a simple 0.
Yeah. So
Вот это выражение имеет 0 второго, именно строго второго порядка, а никак иначе. Это понятно или нет? Не меньше. Я понимаю. Или есть сомнения? Согласен еще раз? Можно почему? Еще раз, значит, у dx, ну, во-первых, можно переписать здесь dx от сигма от w, это то же самое, что dx от w.
да, я...
Нет, ты лучше w оставь.
Да, я лучше оставлю W, вот я говорю. Вот так.
Вот, это понятно, да? Потому что сигма определялось так, что x от сигма от w это то же самое, что x от w. Вот, поэтому вот, у нас dx от w. У dx от w в точке P простой ноль. Это определение. Мы по определению брали такие иксы, у которых тоже простые критические точки, которые dx имеют простой ноль. А теперь вот смотрим на эту штуку. Эта штука, понятно, что при W, стремящихся к PI, они совпадают, W и сигма. Значит, там есть, обращается к ноль. Да? Но почему не может там быть кратный 0? А потому что если там есть кратный 0, то это будет означать, что производная у Y там 0. Ну, давайте...
If we have a double zero here, then we have a zero of the derivative of y, so we have a zero of dy, and it is forbidden by definition again.
Ну, смотрите, почему так? Давайте предположим, что W это локальная координата в этой точке, такая, что сигма W это минус W, да? Для простоты. Мы можем всегда выбрать такую локальную координату. Тогда Y можно разложить в ряд по этой координате. Поскольку, ну, мы предполагали, что это тоже не может быть полюс, значит, она начинается с какой-то константы. Значит, C0 плюс C1 W плюс C2 W квадрат плюс и так далее, да? Но теперь смотрим, что здесь написано, вот это разность. Это разница C0 у вас сократится, да, там, ну и все четко сократятся. И у вас останется C1W, да, 2C1W плюс там 2C3W в кубе плюс и так далее. Но это имеет простой 0, если c1 не равно нулю. Правильно? Но если c1 равно нулю, то это и есть условие того, что dy равно нулю. Правильно? А мы требовали, чтобы у y в точках по не было ни полюсов, ни критических точек. Вот.
Yeah. Okay. So summing this up, so finally we have that this prefactor has again simple 0 in denominator, a double 0, and again a simple. This prefactor has a simple pole, and I mean this prefactor has a simple pole. This guy has a double 0. Then this product has a simple 0, so it cancels when we take the residue. And just the same with the second guy here. We know already that omega 01 of W has double 0. And
no, the omega has a double 0. Just the omega itself has a simple 0.
Omega itself has a simple 0, and S of omega has a double 0. Yes. And what?
I'm not sure about that.
No. Stop. S of omega is a linear loop equation. So this guy has at least simple 0, and this guy has at least simple 0. So their product has at least double 0, and therefore product times the prefactor has at least simple 0, and it also vanished by the residue.
Is it okay? Все понятно, сказали, что вот эти члены, они пропадают. Все теряют
в одну сторону, да. QGN and plus 1/2 SS has at least double 0. Yeah.
Но можно просто взять, все могут сами попробовать просто взять. На самом деле рассуждение, оно в каком смысле почти обращается.
Да, а мне кажется, оно абсолютно обращается на самом деле. Вот. Да, мы доказали в одну сторону, но на самом деле оно абсолютно обращается, мне кажется. Тут все переходы равносильны. И в обратную сторону это делается точно так же. И, мне кажется, даже никаких долгов у нас не осталось. Времени на семинар почти тоже не осталось.
В линейных уравнениях у нас 0. Они просто должны.
Еще раз.
Использовали, вот, например, вот здесь в конце использовали.
Вот, только что использовали. Вот прямо вот в самом конце, вот здесь.
Потому что здесь 0. Потому что если не сказать, что здесь 0, а если просто двоморфность, то тогда может получиться вклад вычет, потому что у вас есть полюс у префактора. Вот у этой штуки есть полюс, поэтому если не сказать, что здесь есть
да, вот у этой.
то тогда вычет вам может отразиться.
Да, то есть мы вот это явно, то, что был, по крайней мере, простой 0 здесь, и, по крайней мере, дабл 0 здесь, только что использовали в самом конце. То есть, в общем, мне кажется, все было существенно использовано. Да, значит, в следующий раз мы поговорим про projection property, про свойства проекции, почему оно действительно эквивалентно тому, что у всех WGN-ов, омега-GN-ов только такие полюса, и дальше тоже. По крайней мере, с этого начнем. Так, вопросы еще? Ну хорошо, давайте тогда я остановлю запись.